guys, how you doing? Cool. So today we're going to talk a little bit about solar panels. You guys have probably seen solar panels. You've seen them up on people's houses. They go on buildings. They're pretty cool. They're almost everywhere. This is a little bit of a change in the order from the way that things are listed in the book. We do the solar panel lab now because it's nice and bright and sunny out. It's a beautiful day, so we actually get to go out and enjoy the sunshine and do some science at the same time. If we wait until later in the year, it gets cold and rainy and wet. And first of all, there's no sun to hit the panels, and also it's miserable to be out there. So we're bringing it a little bit forward in the schedule so that it works for everybody. Hey, and this morning actually we have a guest. Dimitri is here to return the forms that you guys filled out last time. So I will turn things over to him for a minute, and then we'll get back to the solar stuff.
Thank you so much. Good morning, everyone.
All right, so let's go through this problem together. So we've got this circuit with a 20-volt power supply and 3 resistors in series, and we're trying to find out the total voltage, total resistance, and total current for the circuit, and then also the voltages and currents through each of these resistors. So if I want to find out the total voltage, do I have to do any calculations for that? No, exactly. The total voltage is just the voltage that's coming from our power supply there. So we can read that right off the board. We can see that's 20 volts. And then for the total resistance, can I just read that from the problem, or do I have to do something?
Just have that one together.
Yeah, I have to create a simplified circuit. And you're right. For series resistors, it's pretty easy. The equivalent resistor is just the sum of the existing resistors. So what would the equivalent resistor be in this case?
10.
Yeah, 10 kilo ohms. Perfect. And I like to draw out a simplified circuit. When we're working with a circuit like this that just has a single branch with 3 resistors in parallel, it's not hard to see the simplified circuit, but it's a good practice because when we start getting into more complicated circuits with more branches, we want to be able to analyze those as well. And with those, it helps to draw out simplified versions of the circuit. You might have to do 2 or 3 steps of simplification before you get down to just a single resistor. So it's good practice to get into now, and it'll help us out later on. All right. So we have a single resistor here of 10 kilo ohms. This is still a 20-volt supply there. So if I wanted to figure out the current for this simplified circuit, could I do that? Mm-hmm. Yeah. What law would I have to use? Ohm's law, exactly. So Ohm's law is like this, V, I, and R. So in this case, I'm trying to figure out the current. So I write down I equals, and then I cover that up, and I see it's V over R. So what voltage do I have in this case? Yeah, 20 volts. And then the resistance is our equivalent resistance here. That's 10 kilo ohms. So can I just write 10 kilo ohms and divide 20 by 10?
No.
No, why not?
You gotta go by 10,000.
Right, I want to convert this 10 kilo ohms into raw units before I do the math. So instead of 10, I'd write 10,000 like you said. So if I divide 20 by 10,000, what do I get? Yeah, so if you put that on your calculator, you would get 0.002, and and that comes out in amps. And then you can do that conversion and write it as milliamps. You have to move the decimal point 3 places to the right, and you're left with 2 milliamps. Right? So for this circuit here, we can say that the current is 2 milliamps. And since this circuit behaves the same way as this other circuit, we can say that the current up here is also 2 milliamps. So we can write that as our total current, 2 milliamps. Okay? Questions about that? Yeah?
Do you have to write it in 2 milliamps, or can you just write it as 0.002 amps?
You could write it as 0.002 amps as well. I don't mind which way you choose as long as you put the units on there. So you could write 2 milliamps or 0.002 amps, but not 0.002 milliamps, right? So either way is fine with me. And then now we have to find the current through resistor 1, through resistor 2, and resistor 3. So do we have to do math for this? No, we don't. Because the current only has one path that it can go down, right? If the current branched out into 2 or more paths, then some of it would go left and some of it would go right, and you wouldn't necessarily know how much was going in each direction. But since there's only one path for it to flow down, all of it must flow down that path. So if we have 2 milliamps up here, we also have 2 milliamps through every other part of this circuit. Does that make sense? Okay, so we've got the same current flowing through every part of this circuit. We've got 2 milliamps there, 2 milliamps there, and 2 milliamps there. Okay. So that means that we can write over here 2 milliamps for the current through R1, 2 milliamps for the current through R2, and also for the current through R3. And this brings us back to one of those rules that we learned about series circuits. We said that in series circuits, the current is the same for every element in that circuit, right? But what about the voltage? Is the voltage the same for every element? No, right, it's different. It can be different for each element. In parallel circuits, it works the other way, right? In parallel circuits, the voltage is the same for every element, but the current can be different. But we're dealing with a series circuit here. So we figured out that the current is the same for each one. It's 2 milliamps in each case. Now we have to figure out the voltage. So we can use Ohm's law for that again. So in this case, we'll start with R1 here. We want to figure out the voltage for R1. So we write down V equals, we cover that up, we see it's I times R. So in this case, I was 2 milliamps, but since we're using it in a calculation, we're going to write it out as raw units, right? So 0.002 amps times the resistance here, which is 2,000 ohms. So if you multiply 0.002 by 2,000, what do you get?
4 volts.
4 volts, perfect. So we can say VR1 is 4 volts. And we can do a similar thing for R2. It's still 2 milliamps flowing through it, but in this case the resistance is 3 kiloohms. So we multiply 0.002 by 3,000, and we get 6 volts. Right? And then, again, a similar thing for the last one. Still 2 milliamps flowing through there, but now we have 5,000 ohms. So that comes out to be 10 volts. So that's what we were trying to figure out. Any questions about that? Okay, cool. So we'll do some more practice like this at the beginning of other lectures. I highly recommend that you go through this stuff because this is the type of problem that you'll see in other classes and in midterms and in a job if you go out and work in the electronics industry. So this is very important stuff. Okay? Cool. All right, so today we're going to talk a little bit about solar panels. These are very cool. They allow you to generate your own energy. You can put them on your house, on businesses. You can put them on RVs, boats, anywhere that you need power. You can take them backpacking with you if you want to do that. So these are really cool. If you guys do the lab today and you get really excited about this, there's good news. We have a whole solar program. It's a 3-semester long series of courses, and it talks all about solar and solar panels, solar installation. It really gets into the nuts and bolts of how this stuff works. It runs 3 semesters in a row. So the first semester is basic, and then intermediate, and then advanced, and it runs in cycles. So the courses are only offered once every 3 semesters, right? But luckily for you guys, the cycle is starting over next semester. So if you get really interested and you have some time, you can start up with this stuff next semester. So today we did a brief review of series circuits. We talked a little bit about parallel circuits as well. We're going to start our lecture on solar panels by talking about solar cells. These are the little elements that actually make up solar panels. A panel is actually an array of these little solar cells that all work together. So we'll talk about that. We'll talk about the sun because, of course, solar panels absorb their energy from the sun, and we wouldn't be able to do much without it. We'll talk about a day star meter, which is a little meter which allows us to measure the amount of sunlight which is hitting any particular spot, and that will help you if you want to evaluate a location for solar panels. We'll talk about the importance of the panel angle and how just a little bit of a change can really affect the efficiency of your panels. We'll also talk about the fact that panels are much more efficient when they're cold and why that is important. And then we'll do a little bit of solar panel math. Okay? Basically, each panel is cool by itself, but they don't. One panel by itself is not necessarily going to get the job done for you. Okay? These panels create about 18 volts of electricity. And that's enough for charging a car battery or something like that, but it's definitely not enough to run a house, right? A house needs about 120 volts of electricity. So we'll talk about how you can put panels together and make them work for you to create larger voltages and larger currents that you might need depending on your application. Okay? And then we'll go into a brief preview of today's lab. Like I mentioned earlier, we're actually going to get to go outside and play with some real panels today and see how they work. We'll do some measurements with them, and I'll tell you a little bit about that at the end. So, any questions before we get going? Cool. Okay. So let's talk a little bit about solar cells. If you look at a solar panel, it's kind of a rectangle here. And then inside of the rectangle, there are all these little bluish gray smaller rectangles. And they're all lined up like this. And then they've got this wire, this silver wire that goes down the middle of all of them. Okay? And these continue on, all the way down to the bottom here. And there are several rows of these. So I'll pass these around so you can see what I'm talking about. Each one of these little, these smaller rectangles is called a solar cell. Okay, I'll start this one over on this side. I'm not going to pass the big one around because it's heavy and it's fragile, but you guys can come take a look at it at the end. So these little bluish gray rectangles are called solar cells. These are the things which actually generate the electricity. Each solar cell creates about half a volt of electricity. So if you count the number of solar cells on these panels, you should see that there's 36 on each panel. Okay? So even though one panel is small and the other one's bigger, they have the same number of solar cells on them. So they should generate about the same amount of voltage, right? So if they have 36 cells on there and each cell produces half a volt, how much voltage should each panel create? What's that?
18.
Yeah, about 18 volts. And if you look on the back of the panel, you should see that that's what it's rated for. There's a little, a little inscription back there, and it should say that it's rated for about 18 volts. So I think some of them say 17 or 17 and a half. Basically, you lose a little bit of efficiency when you have a bunch of these put together. But it comes out to be about 18 volts. So why would you need a bigger solar panel if you could get 18 volts out of a smaller one? Any idea?
More current?
Yeah, more current, exactly. Even though they create the same amount of voltage, the bigger one creates more current. So you can do that. So you might wonder how these little cells can work together to create a higher voltage. And we'll see that. We'll talk about how that works when we get into the solar panel math at the end. Okay? It turns out that just as these smaller cells are put together to create a larger voltage and current in one panel, the panels can actually be put together as well to create a larger voltage and current from an array of panels. Okay? So we'll talk about that when we get to the solar math. But now let's talk a minute about the sun. Okay? So if you want to talk about how much energy is hitting a panel at any particular time, it's good to have sort of a reference. Okay? And that reference that we use is the amount of energy that would be hitting 1 square meter if the sun was directly overhead on a bright, clear day. Okay? So if the sun is shining straight down on you, there's no interference, and it hits a square meter, we call that 1 sun. And we say that the intensity of light is approximately 1,000 watts per square meter. So 1 sun is 1,000 watts per square meter. And we have little devices little instruments that can measure how much intensity is hitting any particular spot. Yeah?
How much of that power can the solar panel actually absorb?
Not very much. There's new technology coming out every day to make the solar panels more efficient, but right now they're pretty inefficient. I think down below 10% efficiency. What's that?
I think we're on like
15, 20? Okay, so it's better than last time I checked. But yeah, still nowhere near 100.
Wow.
So.
Rachel gets up to like 80.
Oh yeah. Yeah, and there's many things that can affect that, such as the angle, the temperature, yeah, the cleanliness. In fact, if you get a lot of dust or dirt settling on the solar panel, that can really take it down.
clouds.
Yeah, clouds, shadows, sure. Yeah. So we have little meters that can actually measure how much sunlight is hitting any particular spot, or how much of any kind of light. So if we were getting 1,000 watts per square meter of energy out on a bright, clear, sunny day, how much energy do you think we're getting per square meter inside, just from the overhead lights here? Any ideas?
100.
Okay, 100. Any other guesses? 5? Okay. Anybody else? Yeah, I don't know if they're fluorescent, so
Yeah.
not 100% sure. Anyway, right here where I'm standing, 3, 2 or 3, yeah, okay. So, that shows you that the intensity from the sun is pretty strong. Okay. If I hold this up a little bit closer to the light, oh yeah, it gets up to about 5, right? But now if I tilt it just a little bit, like that, it's back down to 3. Okay, so the angle can have a big effect. If I step outside here for just a moment, we should be able to get some sun. Yeah, outside here. So I'm out here, I'm getting about 850, 946. So yeah, so 934 here. So, and now we're back to 3. So, yeah, so the sun is really, really powerful, is the moral of the story. And these meters can help us measure how much power we're actually getting. Okay, so if you were going to go out and decide whether a particular site was good for solar panel installation, you might bring along a meter like this with you to see how much energy was actually hitting a particular spot. Okay. So yeah, just a few degrees off from directly pointing at the sun can make a huge difference in the amount of energy that you're actually absorbing. That's not just true with the meter, that's true with the panels themselves. So when you guys go out and actually do your measurements today, you probably want to work in teams. So one person can be holding the panels and pointing them straight at the sun, while the other person is looking at the meter and taking the data. Okay. If you're trying to hold the panels and write down at the same time and look at the meter, it's going to be really hard for you. So I encourage working in teams. The temperature can also play a big role in determining the efficiency of these panels. It turns out when the panels are colder, they're more efficient. And this seems like something that is sort of trivial and not that important, but it actually is. It can really have a big effect. I heard a story about a company that designed a solar array to go in Colorado, and they designed this during the summertime. They found the location. They got it installed in the fall and everything. They tested it out. It worked great. But then winter came along, and one night there was a big snowstorm, and the snow settled on the ground everywhere, and the snowstorm ended and cleared up, and the next morning it was a bright sunny morning out. And if you guys have ever been out in the snow, you know that when you have a big white sheet of snow like that, it reflects all of the light that's coming down onto it. So suddenly all these solar panels were getting light bouncing into them from all of the snow as well as from the sun above. And not only that, but the snow was keeping everything nice and cold, all right, including the panels. So it was really bumping up the efficiency of these panels. So the company hadn't taken all of that into effect when they designed it. They had designed it for, summertime or fall, and that's when they did their testing. And so they didn't build in enough extra capacity to hold the energy that would come when everything was cold. So on this bright sunny morning, with the snow all around and the chill in the air, these panels were working overtime, and they actually blew out the whole farm because it was just so much energy coming out of everything. So, the temperature can actually have a big effect, especially in areas where you get snow.
How did they blow out the car on fire, or did the battery bust?
I'm not exactly sure. It could have been the batteries were not enough to handle, or it could have been that the cables were not large enough to hold that much, to handle that much electricity. I'm not 100% sure, but it was not good, as far as I know. So, so you do need to take the temperature into effect when you're designing and installing these systems. Okay. So let's talk a little bit about solar panel math. Let's talk about how these solar cells can work together and how solar panels can work together to create higher voltages and currents when you need it. Okay. So it turns out that solar panels act a lot like batteries. They create voltage and current just like batteries. So we can actually treat them like batteries. And the good news for you guys is that you get kind of a 2-for-1 lesson today. We're going to be talking about solar panels, but all of the information that you learn here applies to batteries as well. So you can use it in both cases. Okay? And for the purposes of the simplicity of drawing these things, I'm actually going to draw them so that they look like batteries. All right? They've got a positive terminal and a negative terminal, just like batteries. So I'm going to draw it so that it looks like a battery. So this is the positive side, and this is the negative side. Okay. So each panel produces a certain amount of voltage. Now, different panels can produce different amounts of voltages, but for the sake of drawing these out, I'm going to say that each one of these produces 5 volts and 100 milliamps. Okay? That corresponds to approximately the voltage and current that you'll be getting out of these little panels that you'll be using today for your lab. Okay? So we're going to work with that. Of course, you could substitute different numbers if you had a different situation, but we'll just use 5 volts and 100 milliamps today. All right? The principles are all the same, regardless of how much voltage and current you have. So each one of these produces 5 volts and 100 milliamps. So what would happen if you hooked 2 of them together in series? Say that you measured the voltage there. How much voltage do you think you would see?
10 volts.
Yeah, 10 volts. Okay? So let's see why that would be. We'll call this part ground, so we'll say that this is 0 volts. Okay? And then we look at our circuit and we see that we've got a 5-volt solar panel here. That means that the top of the solar panel is 5 volts higher than the bottom of the solar panel. Okay? And we know that the bottom of the solar panel is at 0 volts. So what voltage do we have at that point right there? 5 volts. Now we can do the same sort of thing up here. We know that the top of this solar panel is 5 volts greater than the bottom, and we know that the bottom is at 5 volts. So what would be the voltage at the top?
10 volts.
10 volts. Exactly. So if we measured between these 2 points, we would see that there was a 10 volt difference between there and there. Okay? So when we put the panels in series, the voltages add together. Okay. What about the current? So, yeah, it'll stay the same. Each one of these says that 100 milliamps has to flow through it. Okay? So that means that you've got 100 milliamps there, and then the other one has 100 milliamps flowing through it as well. So 100 milliamps flows out of the first one, flows into the next one, flows out. So you end up with 100 milliamps flowing along that part of the circuit. Okay? So in series, the voltages add, and the current stays the same. Okay. Yeah.
How much current do you need for a solar panel on a house?
Well, I mean, I think in general, the more current you get, the better. Because if you don't use it for your house, you can sell it back to the electrical company. So, as much as you can get, I guess. Yeah. Yeah.
Since there's more than one manufacturer of solar panels,
Right.
they're not all going to be exactly the same.
Right.
Of course, there's proprietary differences, things like that.
Right.
Obviously, I would imagine you would try to match the currents so that way all of your panels have the same current.
Right.
But if you don't, how would you have your currents then? If you were forced to use different manufacturers together.
Right. So, like, you had one that was 100 milliamps, another one that was 50 or something.
Yes.
I think you would not want to put them in series in that case.
Yeah, you would use a combination of series and parallel circuits. My parents live off the grid, so.
Oh, okay. So you're familiar with this stuff.
Yeah, with some of them, they usually hook 4 of the smaller solar panels together, and then those hook in parallel into the system.
Mm-hmm. Yeah. So we'll see in a minute how you can bump up the current using parallel. So like you mentioned, you could do a series and parallel combination like that. Yeah. But you wouldn't just want to hook a 50 milliamp directly in series with a 100 milliamp, because that, I think, could damage the lower current panel. All right. So in series, the voltages add up and the current stays the same. So when we're measuring the voltage here, we're measuring the voltage when there's no connection between these 2 points. So we call that an open circuit voltage, okay? Because when you have no connection, that's called an open circuit. So this would be the voltage that you would get from the panel if it was not connected to anything. When we're measuring the current, we hook up the meter like this. And we measure current there. Now remember, the meter in the current measuring mode acts pretty much like a wire. So what do you call it if you have a wire from power to ground in a circuit? Well, that's a short circuit, right? Seriously, when you have a wire that goes from power to ground, or some straight path from power to ground like that, that's called a short circuit. So when we measure the current this way, this would be the amount of current that you would get in a wire going straight from power to ground. So we call this the short circuit current, because it would be the current that you would get in a short circuit. Okay? With small panels like this, it is, in the range of a couple hundred milliamps. It's not going to be too much. With big panels, you would have to be careful when you're measuring the current this way, because that could be a whole lot of energy. All right? So in any case, we call it the open circuit voltage and the short circuit current that we measure for these panels. All right? So let's talk about hooking up panels in parallel. Again, we've got 5 volts and 100 milliamps there. And we'll call this part ground, or 0 volts there. So so how much voltage would you have up here at the top of our circuit? 5 volts, exactly. You start off at the bottom at 0 volts, you go up by 5, so you have 5 volts there. Now voltage is constant along any wire. So if you've got 5 volts there, you've got 5 volts there, and 5 volts there, because they're all connected by a single wire, right? So, and the same goes for the bottom as well. You've got 0 volts there, so we have 0 volts there, because it's connected by a straight wire. So, if we measure the voltage on our output, we would have 5 volts. So we can, these are in parallel, so we can say in parallel, the voltages stay the same. Right? Each one of these has 5 volts by itself, and the total output voltage is also 5 volts. So the voltages stay the same. But what about the current? So here we've got 100 milliamps flowing out of this panel, and it flows over here. And this panel is also producing 100 milliamps there. And then these two streams of current are joining up. So how much do you think we have coming out? How much current would we have?
200.
200, exactly. So we had 100 milliamps from each panel, and we have 2 panels, we get a total of 200 milliamps. So we can say that in parallel, the currents add together. Okay. So in parallel, the voltages stay the same and the currents add together. Whereas in series, the voltages add and the currents stay the same. Okay. But now, so far we've seen how we can bump up the voltage and we've seen how we can bump up the current. But what if we wanted to do both, right? So say that we wanted to have a circuit that produced 15 volts and 200 milliamps. So we want to increase the voltage and the current. Again, using these same panels that we have. Do you think it would be possible to do something like that?
Mm-hmm.
Yeah. What could we do?
Add two more in series.
Yeah. So we could increase the voltage by putting some panels in series like this. So if we have 3 panels in series, we said that that would be 15 volts, right? We know that that would be 15 volts because each one is 5 volts, right? And then we can increase the current by putting another row of these in parallel. Okay, so let's work through this and see how this works. We're going to call this bottom part 0 volts down there. So how much voltage do we have at this point? 5 volts, perfect. Up there, how much? 10 volts. And right there, what do we have? 15 volts, perfect. So we got that 15 volts that we were looking for. And now we said that each one of these panels has 100 milliamps flowing through it, right? So that means that we have 100 milliamps flowing out of the top here, and also 100 milliamps flowing up from this part, and those two streams join together, so they combine, and you get 200 milliamps flowing out down that wire. Okay? So by using a series and parallel circuit, we are able to create higher voltages and higher currents. Oh. Any questions about that? Okay, cool. All right, so that was the solar panel math that I wanted to talk about. We talked a little bit about series, a little parallel, and then a little bit of series and parallel. So let's go on to a preview of today's lab. So this is really cool. You guys are actually going to get to go outside and play with some solar panels in the beautiful outdoors. It's a wonderful, gorgeous day out there today. So you guys are each group of you will get a set of 4 solar panels that look like this. Okay? And you're going to be using these for your experiments. So the first thing I wanted to tell you about these is that when you are doing the experiments, you have to be careful about how you hold the solar panels, right? A lot of people will go out and hold the solar panel like this. This is a natural way to hold it, but there's a big problem because you're covering up one of these little solar cells, okay? And all of the solar cells or a lot of them, are arranged in series. So if you block one of the cells, you're blocking that entire series of cells. Basically, it's like creating an open circuit. So just holding it like this is going to mean that this panel is no longer creating any voltage or current. All right. So when you hold them, you want to make sure you hold them from the sides and expose the entire front to the sun. Okay. So be careful about that. These panels have served us well for a long time, but just this past week, we started noticing that a few of them were generating lower currents than we expected. So we expect that on a bright sunny day like today, you should be getting at least 100 millivolts out of each of these panels. You guys will do the measurement and find out exactly what it is, but it should be at least 100 millivolts. Or milliamps, I'm sorry. If you start seeing currents in the 25 or 50 milliamp range, then something is wrong, and you should tell me or one of the other lab techs about it, and we will help you. We'll get you a different panel. All right. So at least 100 milliamps. So you're going to be putting these panels together. You're going to be measuring them individually first, and then you're going to be putting them together in series and parallel combinations to see how they work. The lab for today is on page 151. You don't have to take out your book right now, but when you go to do it, that's where it is. So the first thing you're going to be doing in the lab is that you're going to be measuring the solar panels and seeing how they behave individually. So you're going to measure each one. It says to do them all inside, but it's actually better to do them outside. All right. So there's a table where you're going to note down the current and voltage for each panel. So take the panels outside when you do that. All right. The second part asks you to do a parallel circuit. All right. So you're going to start off with two panels in parallel, and you guys remember that parallel means that components start at the same place and end at the same place. So in this case, we're going to say that the start of the panels are the black wires. So you're going to connect all of the start of the beginning of each element together. So you're going to tie all of the black wires together, okay? And then we're going to say that the panels end at the red wires, so we're going to tie the red wires together, okay? And this leaves you with two open ends, all right? So when you measure the voltage and current, you're going to hook your meter up to these open ends, all right? And one person is going to hold the panels and point them directly at the sun, trying to keep the angle as close as possible to the sun. The other person is going to read the value off of the meter and write it down in your book. Okay?
So that's going to be a parallel?
Yeah, yeah. And you have all of the red wires connected to all the other red wires, and all the black wires connected to the other black wires. That's parallel. So you can do this for 2 panels. You can do it for 4 panels as well. You just add on more panels and wire all of the red wires together and all the black wires together, and then they're in parallel. Okay. And then you're going to next hook up the panels in series. So you're going to disconnect everything. And then you remember that series means that elements are connected end to end, almost like trains on a train track, right? The start of one element is connected to the end of the next one. So the easiest way for me to think about this is you just lay the panels out in a row next to each other, okay? And then you have to hook them all together. So you take the red wire from the first panel and connect it to the black wire of the next one. And then you take the red wire from the second panel and connect it to the black wire of the third one. So you just keep going like that, red to black, red to black. All right, and that's in series. And then when you're all done making your connections, you're going to be left with the two wires from the ends. And these are what you're going to use for hooking up your meter. Okay? So you're going to hook one side of the meter, or the black lead from the meter to the black wire, the red lead from the meter to the red wire. Okay? When you're hooking up your meter, you have to be sure that you're using the correct locations. So for measuring voltage, you're going to be measuring with the red wire in the far right-hand side where it says V. Black wire is always going to be in common, like it always is. When you're measuring current, you have to move the red wire over, and for small currents, you're going to be using the milliamp setting. Right? So this is good up to about 200 milliamps. Now, if each of these panels is producing, say, 120, call it 120 milliamps, and you hook up two of them up in parallel, how much current are you going to get altogether?
360.
Well, two of them.
Oh, 240.
Yeah, 240. Right? So can you measure that much current in the milliamp setting? No, right? It only goes up to 200. So when you have two or more panels in parallel, you have to move the red wire over to this 10 amp setting. Okay? And when you do that, you have to put the dial in the 10 amp position. Okay? There's only one position on there that says 10 amps. That's the only position you can use for measuring current in the 10 amp setting. Okay? So you'll have to use the meter like this for measuring more than one, or for measuring two or more panels in parallel. Okay. All right. So in part 3 of your lab, you're going to in part 4 of your lab, you're going to actually design your own solar panel array. So you're going to do something like we have up here on the board. The book will ask you for a specific voltage and current output, and then you'll have to figure out how many solar panels it would take to do that, and what configuration you could use to get the voltage and current that the book is looking for. Okay? When you do this, you should assume that the solar panels are each creating 5 volts and 100 milliamps. Part 4, number 3 says that you should actually build the circuit. You can ignore that part. You don't have to build it. You just want to design these. You don't have to actually put them together. If you're feeling really excited, you can try it out, but you don't have to. Okay? And then that's pretty much it for this lab. It asks you to list 3 things that you learned in the lab, and explain why it's so important to hook the panels up correctly to get the voltage and current that you want. So that's pretty much it. Any questions about the lab? Okay, cool. Then let me take attendance, and I'll let you go.